Hello everyone, welcome back to Math with Allison. Today we're continuing our integration series, so we're going to be talking about the proof of the fundamental theorem of calculus. So let's go ahead and dive into it. First we're going to define the area function. So let f be a continuous function for t is greater than or equal to a. The area function for f with left endpoint a is a of x equals the integral of a to x of f of t dt. So x needs to be greater than or equal to a. The area function gives the net area of the region bounded between the graph of the function and the t-axis on that interval. So I have a picture of what this looks like right here. We have an example. We have our function f of t is equal to 2t plus 3. So we're going to go ahead and start at 2, and we're finding the area all between 2 and x. So usually we're used to this right endpoint being a number rather than x, but this is just showing that we can choose any value there, and we're going to be able to find that area. So let's go ahead and calculate this without using integration. So if we remember, this is actually going to be the area of a trapezoid. So let's go ahead and find all these values. Let's go ahead and first find this height right here, because remember, we need to find both of these heights. So what I'm going to go ahead and do is take our 2 and plug it into our function. So here we have f of 2 is equal to 2 times 2 plus 3. That is equal to 4 plus 3, which gives a height of 7. So we have this first height is equal to 7. Now, when we find the second height, all we're doing is plugging an x into our function. So f of x is equal to 2x plus 3. So here we have this other height is 2x plus 3. So now we have both heights. Let's go ahead and find the base as well. So the base is going to be this length right here. So what we do is we take the entire length, and so this whole thing is going to go out to x. And we want to go ahead and get rid of or subtract this second little area right here, which is going to be a length of 2. So I know this entire length right here is going to be x minus 2. So now we have both our heights and we also have the base of it. So if we remember, the area of a trapezoid can be found as 1/2 base times height 1 plus height 2. So let's go ahead and plug in what we know. We know the base is going to be x minus 2, and we know the first height is 7 and the second height is 2x plus 3. So let's go ahead and start simplifying this out. We get 1/2 x minus 2, and that becomes 2x plus 10. I'm going to go ahead and FOIL first. I'm going to multiply those two together. I get 2x squared plus 10x minus 4x minus 20. Let's go ahead and combine those x's. So we get 2x squared plus 6x minus 20. And then we can divide everything by 1/2. So that becomes x squared plus 3x minus 10. So here we got the area of this function is equal to x squared plus 3x minus 10. Now let's go ahead and do this using the definition that we just talked about. So instead of using the area of a trapezoid, we're going to go ahead and set up the integral. So a of x is equal to the integral from our left endpoint. Our left endpoint is going to be 2 all the way up to x. And then on the inside, we have our function, which is 2t plus 3 dt. So let's go ahead and calculate that. First, we're going to go ahead and take the antiderivative. So the antiderivative of 2t is going to be t squared. The antiderivative of 3 is going to be 3t. And this is going to be from 2 all the way up to x. So now we're going to go ahead and plug these in. So first we do upper. So we get x squared plus 3x. And we have to subtract the lower value plugged in. So 2 squared plus 3 times 2. Let's go ahead and simplify that. We got x squared plus 3x minus 4 plus 6, which we know is going to be equal to that value 10. So our two areas matched up. So what would happen if we were to take the derivative of our area function? So a prime of x is equal to 2x plus 3, right? Which is very similar to what we were integrating. We were just integrating in terms of t rather than in terms of x. And so this is going to give us a little hint. So we're going to actually go ahead and prove why that's the case. So let's go ahead and go through the proof of it. First, I have a random function. We have f of t. Our variable of interest is going to be t in this case. And I have our first endpoint is a all the way up to x. So the area between the curve and the t-axis is going to be a of x as labeled. So now what would happen if we added on some little distance of h? So that right there is going to be h, and our new point becomes x plus h. And so now if we take that entire area, that's going to be the area of x plus h. But I want to go ahead and isolate that new little area we got. So in order to do that, I'm going to take my big area, a of x plus h, and I'm going to subtract off my little area. So it's like if I took my big area, a of x plus h, and I subtracted off this whole area right here. All that we would be left with is this area, as we can see in that last photo. So I can go ahead and estimate this area actually using a rectangle, right? So if I make this whole thing my rectangle, I have my height is going to be f of x, and now my length is going to be that little distance of h. So I can go ahead and estimate this is about equal to f of x times h. But I want to get f of x all by itself, so I'm going to divide over that h. So here we get a of x plus h minus a of x all divided by h is approximately equal to f of x. Again, this is not perfect because we're using a rectangle to estimate the area. But in order to make it a lot more accurate, let's go ahead and take the limit as h approaches 0, because the smaller the rectangle gets, the more accurate it gets at predicting the area. Now, notice on this left side, this is a definition of a derivative. It's a limit definition. So right here, I get a prime of x, or the first derivative of our area function, is equal to the limit as h approaches 0 f of x. Notice here, there's no h involved in f of x, which means we're not taking the limit of anything. So this is just going to be f of x, which just proved what we did up here, right? We get a prime of x is equal to 2x plus 3. So let's keep doing this. So I know this is the first derivative of our area function, but we already defined our area function, so I'm going to go ahead and replace that. So here we have the integral from a to x of f of t dt. But we already know what this is equal to. We know this is equal to f of x. So what we do when we differentiate an integral is we take our function, which we are taking the integral of, and we just plug in our variable, which is very nice, right? And that's the proof of the fundamental theorem of calculus. So here we have it listed out very nicely. If f is continuous on an interval a to b, then the area function, which we already defined earlier, is continuous on ab and differentiable on ab. The area function satisfies a prime x equals f of x. So here we have what we had just written out. We get the a prime x equals f of x, which means that the area function of f is the antiderivative of f on ab. So here we have another example to work through. We have find the derivative of the integral of that function. But remember, now we know how to actually do this. All we do is we take what's inside the integral. So we have sine of t, but instead of t, I'm going to go ahead and plug in my variable, which is going to be x. So I get sine of x times cosine of 2x. And that is how we differentiate integrals. So the most applicable part of the fundamental theorem of calculus is right here. If f is continuous on a to b and capital F is the antiderivative of f on ab, then when we take the integral of a to b of f of x, that means we take the antiderivative and we plug in the upper value and we subtract the plugged in lower value. So let's go ahead and go through an example of that. We have the antiderivative of 1 to 2 of 2x dx. So our first step is to find the antiderivative of 2x, which is going to be x squared. And we can check that because the derivative of x squared is equal to 2x. So I know that's the antiderivative. And we are working on the interval from 1 to 2. So what we get to do is we get to plug in the upper value. So we do 2 squared, and we subtract the lower value plugged in. So when we write that out, we get 4 minus 1, which is equal to 3. And this value represents the area between the function, which is 2x, and the x-axis between 1 and 2. So that's all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.